Hi everyone, I'm Claire, and today I'm going to be presenting on Euclid's Book 10, which deals with irrational magnitudes. So a little overview on Euclid's Book 10 is that he focuses on proving the irrationality of non-square numbers such as the square root of 2. So he introduces the concept of irrational numbers, and he produces a formula to find Pythagorean triples, as well as he explores incommensurables. So with irrationality, Euclid defines irrationality as a number is irrational if it cannot be written in the form p divided by q for some integers p and q. This means that if a number is rational, then it can be written in the form p divided by q for integers p and q. So Euclid is going to use the properties of rational numbers to prove by contradiction that the square root of 2 is irrational. So looking into how Euclid proves that the square root of 2 is irrational, what he's going to do is he's going to start by assuming that the square root of 2 is rational. So using the definition of rational, he's going to say that the square root of 2 equals p divided by q for some integers p and q. This means that 2 is going to equal p squared divided by q squared by squaring both sides. Then he can say that 2q squared equals p squared by multiplying both sides of that equation by q squared. From there, he can say that we know that p squared is going to be an even number since it equals 2 times q squared. So we can say that p squared equals 2m for some integer m since p squared is even. Then we can say that 2q squared is going to be equal to 4m squared by substituting p squared, by substituting 2m in for p squared, since they're equal. And then by dividing both sides of that by 2, we can say that q squared equals 2m squared. Then we can say that we know q squared is going to be an even number, since q squared equals 2m squared. So since it's even, we can say that q squared equals 2n for some integer n. Lastly, we can say by substituting 2m and 2n in for p and q in our original equation, we can say that the square root of 2 is equal to 2m divided by 2n, which equals m over n. So now we're back where we started, where we have the square root of 2 equals an integer divided by an integer, only we simplified it. By using this same process, we can continuously do that and continuously simplify our expression by just repeating the cycle over and over and over again, and we'll just keep ending up with 2 different integers in a more simplified form of the square root of 2. We don't know what these integers are. They just represent, they could be any integer, but we know that it's continuously being simplified. So then knowing that that's not possible to continuously simplify a number over and over and over again, we come to a contradiction. So from there, we can conclude that the square root of 2 is irrational, because if it was rational, we come to an illogical conclusion. I'd also like to note that there are plenty of other ways to prove that the square root of 2 is irrational. This is just the way that Euclid approached it. So Euclid also talks about the concept of Pythagorean triples in Book 10. And so what Pythagorean triples are is they are a set of 3 positive integers, A, B, and C such that the formula a squared plus b squared equals c squared is satisfied. And so we typically will denote a Pythagorean triple by a comma b comma c in parentheses. So some common Pythagorean triples, many of them you guys may be familiar with, are 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. So all of those numbers, if you plug them in for a, b, and c in the formula a squared plus b squared equals c squared, they're all going to satisfy that equation. So one thing that Euclid did was that he found a formula for finding Pythagorean triples. Because if you look back at this list over here, a lot of them are just kind of random pairings. And if you look at that formula, it can be hard to find numbers that are integers that are going to perfectly match up and perfectly, fill that equation. It's easy to pick 2 and find a third, but it's hard to pick 2 and find a third that is also a rational number, or more specifically, a positive integer. But oftentimes, if I just pick 2 integers for a and b, and then I solve for c, oftentimes we're going to find that c is going to be an irrational number. So this is how Euclid went about finding Pythagorean triples such that they, were all integers, because that's what makes it a Pythagorean triple. So the formula that he came up with was that if you're given integers m and n such that m is greater than n, which is greater than 0, then your a in your Pythagorean triple is going to equal m squared minus n squared. Your b is going to equal 2mn, and your c is going to equal m squared plus n squared. So if we consider m equals 2 and n equals 1, you can see that we would have a equals 2 squared minus 1 squared, which equals 3. B is going to equal 2 times 2 times 1, which equals 4. And c equals 2 squared plus 1 squared, which equals 5. So that's going to leave us with the Pythagorean triple 3, 4, 5, which is a very common one that I'm sure you all have seen in trigonometry. And anytime you do geometry, that one typically comes up a lot. And so you can see here that that's how you get it. And a lot of the other Pythagorean triples you can also get from this method using different values for m and n. So a way to find more Pythagorean triples once you're given a Pythagorean triple is, say you have any Pythagorean triple a, b, c, and some integer k, such that k is greater than 0. Then you can find another Pythagorean triple, and that's going to be ka, kb, and kc. And an example of this is, we already know that 3, 4, 5 is a Pythagorean triple. So if we use the k value of 2, then we would get ka equals 6, kb equals 8, and kc equals 10. And if we took 6, 8, 10 and plugged it into the equation a squared plus b squared equals c squared, we would see that it satisfies that equation. And then we can also find, if we have the k value of 3, you'd get 9, 12, 15, which also satisfies the equation. And we can keep doing this for any value of k. K equals 4, k equals 5. And all of those values are going to create more Pythagorean triples. So from here, it's pretty easy to see that there's an infinite amount of Pythagorean triples, because even just from the Pythagorean triple 3, 4, 5 alone, we can, there's an infinite amount, because you can just keep, doing k equals 6, k equals 7, k equals 8, and just keep using more k values. And you're going to keep getting more Pythagorean triples. So then one thing to note is a Pythagorean triple with values of a, b, and c is going to be considered primitive if the greatest common factor of a, b, and c is 1. So what that means is if we look at the Pythagorean triple 3, 4, 5, we notice that there's no number that 3, 4, and 5 are all divisible by. So that means that 3, 4, 5 is going to be primitive because the only number that they are all divisible by is 1. However, if we look at the Pythagorean triple 6, 8, 10, all three of those numbers are divisible by 2. So that means that it has a greatest common factor greater than 1, and thus would not be considered a primitive Pythagorean triple. And it's the same thing with 9, 12, and 15. They're all divisible by 3, not a primitive Pythagorean triple. All right, and the last thing I wanted to talk about was the concept of incommensurability, which Euclid discusses in Book 10. So 2 numbers are said to be commensurable if their ratio is a rational number. So if we look at the numbers 1 and 2, we're going to see that they are commensurable because their ratio, 1 divided by 2, is rational. However, if we're looking at the numbers 1 and square root of 2, those 2 numbers are not commensurable because if we look at their ratio, 1 over the square root of 2, that number is irrational. So thus we can conclude that 1 and 2 are incommensurable numbers. And one thing that I wanted to take note of is that we can have 2 irrational numbers that are commensurable. So in the previous example, when I talked about the numbers 1 and 2 and how they are commensurable, both of those numbers were already rational numbers. And actually, anytime you have 2 rational numbers, they are always going to be commensurable because any rational number divided by another rational number is going to give you a rational number. But you can still have 2 numbers that are irrational that give you a commensurable number. And so, for example, if we look at the numbers square root of 2 and 3 square root of 2, their ratio is going to be square root of 2 over 3 square root of 2. And if we look at that number, the numbers square root of 2 are on top and bottom. So they're going to divide out, which leaves us with 1 over 3, which is a rational number. All right, so that's all I have for this presentation, and here are my sources. Thank you so much for watching.